definition for a non-trivial subspace V. Now, you could define the basis for a trivial space, the zero, as the empty set, but that's a technical thing. I just want to have some intuition behind what the basis is, so I'm going to exclude that. But later in the course, we're going to talk about basis for any vector space, okay? But let's just talk about non-trivial subspace V. An ordered set, or sets are not ordered, right? So if you have if you have 1, 2, 3, it's same thing as 3, 2, 1, or any order, right? These are considered the same. Sets don't have any orders. But if you put parentheses, which is known as tuples or tuples, 1, 2, 3, this is not considered the same thing as 3, 2, 1. So that this is like, it's somewhat like a set, but it has ordering. Ordering is important, okay? So an ordered list of vectors v1, v2 until vd is called an ordered basis this is an important word, basis of V if for any V in V there is a unique way to write V equals to A1 V1 plus A2 V2 A and Vn, AD Vd. And this uniqueness is an important assumption. So let me add to this that this thing here is what's known as a linear combination of V1 until Vd. Okay, so in other words, what this definition is trying to say is that for any subspace V, if you can find a set of vectors where anything in V can be written as a linear combination of these vectors, and it can be done in a unique way, then that's known as such a set. If you give it an ordering, it's called an ordered basis. Okay? that's just another way of writing it, and I still don't expect you to understand what I said fully. You only understand a definition when you've seen a concrete example. Okay? So don't try to tackle something abstract like this as something to memorize or something that fell out of heaven for some reason that you just have to know. That's not how math works. Every definition has a reason for it. Okay, so you want to think of concrete examples, and from there you want to understand what that definition says. Okay, that's the proper way to learn math. Okay. All right. So let's work with that same vector space that we've been talking about before, which is that you have the subspace of R3 where you have x, y, z such that x plus y plus z is 0. So, e.g. Consider, say, 1, negative 1, 0, 0, 1, negative 1, and negative 1, 0, and then 1. Okay. Let's consider this. Then, any v in V can be written as V equals to A times 1, negative 1, 0 plus B times 0, 1, negative 1 plus C times negative 1, 0, 1. Sorry, let me switch things a little bit. I want this one here. Okay, so sorry about that. I want A to be here, and no, that's not going to be good. Okay, I'll put a minus A here, then minus C here, minus B. Okay, forgive me for the weird way of writing this. So the reason, I should really be writing A, B, C, but I'm writing negative B, negative C, negative A, because if you simplify this into a single vector, what do you get? Can you do the calculation? What do you get? Calculate it. Multiply the coefficients into the vector and add them up. Tell me what you get. Come on, say it. Are you waiting because you really don't know? Come on, that can't be true. Tell me what it is.
B minus A.
Right. You get negative B, negative A plus negative A times negative 1. So what's that? That's A minus B. Okay. Then what?
B minus C.
B minus C.
Negative A plus C.
Negative A plus C. Okay, so that kind of explains why I chose these weird numbers, right? Because we already showed that, right? Anything that looks like this, that does this. Right? So does that mean that these three vectors form a basis for this vector space, this subspace?
Yes.
Well, it is able to represent, right?
Right.
But what's not so sure is uniqueness. Is it unique? That's the problem. Okay. So let's just pick any random vector in here. Let's say 1, 1, 2, negative 3. That definitely belongs here, right? Okay. Now, how can we represent this? Let's see. 1, negative 1, 0. 0, 1, negative 1. Then, you know what I'm going to do? I'm just going to put a 0 here. And then I'm forced to say this should be 1. And then negative 1. Let's see. Negative 1 plus 1 is 2, so this must be 3. Does that work?
Mm-hmm.
Okay. Yeah, hopefully you're doing the calculation in your head. You really have to actively participate to understand, okay? Yeah. If you're just sitting there taking notes, you're not going to understand the thing, right? Make sure you do the calculation. 1 times 1 is everything, 0 is nothing, but if you add these two, what do you get? You get 1 times negative 1 plus 3 times 1 is 2, right? Then 1 times 0 is 0, 3 times negative 1 is indeed negative 3, so this does work, right? Okay, but 1, 3, and 0, is that the only way to represent this? Can you think of another? This time, let's put 0 here. Let's see what happens then. In that case, the only way to make 1 as 1, I'll need negative 1 here. What goes here? Figure that out. 2? Yeah, I think so. Right? Negative 1 times 1 gives you negative 1. 2 times negative 1 is negative 2. Negative 2 plus negative 1 is indeed negative 3. So that also works. Oh, so is the uniqueness part true? No, it's not true. Okay? So what we just showed is that indeed every vector in here can be represented as a linear combination of these 3 vectors. In such a case, we say that the 3 vectors span V. So we see that while span of these 3 vectors, 1, negative 1, 0, 0, 1, negative 1, and then negative 1, 0, 1, span of these 3 vectors is equal to V. It does span all of V, right? The set, usually people write B for basis, the list, it's not a set. The ordered list B, 1, negative 1, 0, 0, 1, negative 1, negative 1, 0, 1, is not a basis. It's not a basis. And in fact, if you take any one of the 3 vectors out, then that's going to be a basis, right? So, on the other hand, is a basis. Okay. Now, let's see why. Why is that a basis? Well, first of all, so proof. Span of, so number one, span of this beta prime is indeed V. How do you know? Well, first of all, first A times 1, negative 1, 0 plus B times 0, 1, negative 1. So what am I doing? I'm taking each of the vectors in this list and multiplying some constant in front of it. So I'm doing scalar multiplication for each of the vectors and I'm adding them up. What is this thing called? It's called a
Linear combination.
linear combination. Okay, so I'm taking a linear combination. Yeah. In fact, if you have taken calculus 4 differential equations or partial differential equations, then you've already have seen how powerful linear combinations are, right? Yeah. You take some basic functions and you take linear combinations of them, and you by doing that you can find general solutions. You've done that in those classes, so you probably understand that taking linear combinations is an important thing. Okay. All right, so I'm taking a linear combination. Let's try to simplify this. What do you get if you do this? A comma, what?
B minus A,
Yeah, B minus A, comma,
negative B.
negative B. Okay. So any linear combination of those two vectors satisfy that A plus B minus A plus negative B. So I'm thinking of x plus y plus z. Okay. See, this is x, y, z, right? Let me use a different color. X, y, z, right? So if you add x plus y plus z, in order to be in V, you need this to be 0, right? Yeah, well, what do you get? 0, we do get 0, right? Yeah. So, since it satisfies the, I read the definition of V, but V is a collection of all points where x plus y plus z is equal to 0. So, this means that span of this B prime is a subset of V. Okay. All right. For the next week's quiz, none of the proofs will appear. Okay, we'll do plenty of calculations, and you will have to do that. But eventually, in this class, you'll have to learn how to do proofs like this. Okay. All right. So just to give you some pointers, how do you show that two sets are equal? You say one is a subset of the other, and you also show the other direction, right? So I only showed one direction. I showed that this is included in V. Now we have to show V is included in a span of B prime, right? So let's try that. Next, for any x, y, z is in V, right? Since x plus y plus z is 0, okay, and I'll use this. Y is equal to negative x minus z. Since x plus y plus z is 0, we can solve for y, and then plug it back in here and say x comma y comma z is x comma negative x minus z comma z, which is same as x times 1 comma negative 1 plus z times, 1 comma negative 1 comma 0 plus z times, okay, tell me what goes in here.
0, negative 1, 1.
Good. Oh, this is almost that, right? But all I have to do is change this z to negative z, then this should be positive 1 and negative 1, okay? So this is going to be x times 1, negative 1, 0 plus negative z times 0 comma 1 times negative 1, and this is again a linear combination of these two vectors, right? So this definitely belongs to the span of B prime. Okay. And since I chose any element in here and showed that it belongs here, that shows that V is in the span of B prime. So now I show that these are indeed the same. Okay. Yeah, I'm being too technical here, I think. We're just doing a review and I'm doing something that's more serious. Yeah, just try to absorb as much as you can. That's not the point. The main goal of today is to review the stuff and get more conceptual understanding. But things as hard as this is going to be a regular thing that we're going to do for the next week. So I'm just warning you what's going to happen later, okay? So that's number one. So what this shows is that anything in V can be represented as a span. Okay? But I'm also saying that it has to be unique. Yeah, I just realized that my previous definition of basis is lacking one thing. So I just said that anything in here should be represented uniquely by an element in here, but one additional requirement that I forgot to write is that span can't be bigger than this, okay? There's something technical there, but I see. Yeah, so what I'm missing is that all of individually I need these vectors to be an element of V. Okay, yeah, that's the condition I forgot. Okay, all right. So go back to that original definition that I wrote down, back to notes, and if you're taking notes, if you have VD like that, just say that all of these should be a subset of V. Okay, so that condition is missing. I forgot that condition. All right. Okay, but anyways. So now the second thing is that we have to show uniqueness, okay? So how do we show uniqueness? Well, uniqueness. Suppose A times 1, 1, 1, negative 1, 0 plus B times 0, negative 1, 0, 1, negative 1 is equal to C times 1, negative 1, 0, plus D times 0, 1, negative 1. So in other words, suppose I have two linear combinations which happens to give you the same vector. Okay? Now, to say that this is unique is to show that A has to be C and B has to be D. There's no other way. If we prove that, that means it's unique. Does that make sense? Okay. How do you show something's unique? You say two things are equal, and you show that the only way that this can be true is if A is C and B is D. Okay. So let's write down what that means. So in that case, the left side gives you A, we already did that here somewhere, right? B minus A, negative B, is equal to C, C minus D, no, D minus C, and then negative D. But look, for this to be true, since these two vectors are same, they have to be same component-wise, right? So that forces you to have A as C. And then look at this one. The last part, you see that negative B has to be negative D, right? So that forces you to have B equals to D. Okay? Did we get it? Okay. So that shows you that the this choice, 1, negative 1, 0, 0, 1, negative 1, is indeed a basis. So, another basis. What's another basis? Another basis is, let's say, double prime. Just delete the first guy and keep the other two. Okay. So we have 0, 1, negative 1, and then negative 1, 0, and 1. Okay. Now I'm not going to bore you with details after this, but you can show that this again spans the same V, and it also satisfies the uniqueness. Okay. So that's another basis. Now, this example is kind of important because you can see that in the definition that I wrote down initially, I said a basis for V, meaning that basis is not unique. There are like infinitely many different ways to pick a basis for a vector space V. And you can't, in many cases, you can't say one is better than the other. I mean, if you were to represent all elements in V, would you take these two vectors as the basis or these two? Which would you prefer? I don't think one is better than the other. Like, they're equally good. Now, on Rn, that's a different story. So, example 2, on R3, you have a somewhat natural basis. What's the natural basis in R3?
One zero zero
Yeah.
0 1 0 0 0 1.
That's the natural basis, right? I mean, anything in R3, what's an element in here? It looks like x comma y comma z, right? That can always be represented as x times 1 comma 0 comma 0, y times 0 comma 1 comma 0, plus z times 0 comma 0 comma 1. So we immediately see that anything in here can be represented as a linear combination of these three vectors, and this representation would be unique, right? You can also see that there's no other way to write down this vector as another choice of numbers. This is the only way. So for Rn itself, there's a name for this one. This is what's known as the standard basis, right? This is standard basis. Now, for just R3, because you do this a lot in physics, you like to write it as ijk for dimension 3, and then also dimension 2, people write I and j. But then when you go to higher dimensions, you run out of numbers, so instead of doing it like this, people also use like E1, E2, E3. So E1, E2, E3 are these three vectors. That's how people denote these. And that's called the standard basis. So for Rn itself, there's a natural basis for it. There's the standard basis. But this is not the only one. In fact, you can have many different bases. And you might wonder, why would anyone think about a different basis for the same space? Well, surprisingly, it's useful for many purposes. So, for example, if you record music, then how is music stored in your computer? It's a bunch of numbers, right? And because you have a list of numbers that can be thought as a vector in Rn, and instead of trying to represent that as the usual standard basis, you rewrite it as a sum of Fourier elements. So there's something called a Fourier basis. And if you write it as Fourier basis, then you can kind of set some of these numbers to 0 if it's close enough to 0, and then that allows you to simplify the stored vector, and that allows you to compress the vector. And that's how MP3 is made, right? So if you have a WAV file, you save it as a MP3 file, you save a lot more space by putting a lot of things to 0, and that's how you enjoy music on Spotify. So anytime you listen to music on Spotify, you can kind of have an appreciation that there are other bases other than the standard basis. So it definitely has use cases. Being able to think of other vectors is important. So here's another one. So EG3. So on R4, we have you can have 1, -1, 0, 0, 0, 1, -1, 0, and then 0, 0, 1, -1, and then you can have 1, 1, 1, 1. So you call this as B. Now this is not going to be the standard basis, of course. It's not the standard basis, but this will still be a basis for R4. Okay. Now, as you see more and more examples of basis, there's one thing that does stand out, which is that even if you have two different bases, like this one and this one, they have the same length, right? This is length 2. That's also length 2. Right? Now, in R4, we have the standard basis, E1, E2, E3, E4, right? But here's another basis, and I didn't prove that this is a basis, but this is indeed a basis, and what's the length of this one? 4. Again, 4, right? So the theorem is, which will be proven later in this course, is that the length of basis, any basis of V is same as other. as other bases. Okay. Same as the length of other bases. Okay. And therefore, the length is what's known as the dimension. Okay. So the formal definition, see, we are talking about dimensions without really giving a definition. We were saying that the plane, this vector space V is dimension 2 just because if you look at the geometric object in three-dimensional space, it's a plane, right? But now we have a definition of what a basis is, what a dimension is. Dimension is the length of a basis for that vector space. It's always the same regardless of which basis you take, and that's going to be proven later, and therefore it's a quantity that does not depend on the choice of basis, and that's called the dimension. Okay, so this, we can see that this is dimension 2 just by looking at the size, the length of the basis. Okay? All right. Now let's revisit this uniqueness again. Okay, so let's talk about uniqueness and linear independence. Let's just call this as V1 and V2. And let's rewrite what we were trying to prove here. We're saying that A times V1 plus B times V2 equals to C times V1 plus D times V2. Okay, that's what I wrote over there, right? That's what I wrote. And there's a way to simplify this by moving all the vectors to the left side and combining like terms. So if you subtract CV1 to the left side, I get A minus C V1. And then if you subtract, that's B minus D V2 equal to 0, right? Okay. Now what? What this is saying is that, see, this is, again, some constant. That's, again, some constant. So I can rewrite this as K1 times, let's use C1. C1 times V1 plus C2 times V2 equals to 0. Now, the 0 on the right side is a vector. It's really 0, 0, 0. It's a 3D vector here. And what this result is saying is that if you can show that the only way to write 0 as a linear combination of these two vectors is for C1 to be 0 and C2 to be 0, if that can be proven, then you will see that A minus C has to be 0 and B minus D, which is C2, this also has to be 0, which in turn shows that A has to equal to C and B is equal to D. You see that? Okay, so we have this concept of linear independence. So let's talk about the definition of linear independence. Definition. if the only way for C1 times V1 plus C2 times V2 plus da 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 Cn times Vn equals to 0 to hold is to have C1 equals to 0, C2 equal to 0, da 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 Cn equals to 0. Then we say V1 through Vn, this list is linearly independent. Put it in another way, in other words, so first of all, 0 is in any vector space, any subspace. How do we know that? Because subspaces are closed under scalar multiplication. You take any vector, you multiply by 0, you get the 0 vector. 0 times any vector gives you the 0 vector, right? So 0 is always in the subspace V. And if V1 through Vn does form a basis, then this expression should be unique, right? So you just take the uniqueness part out as a separate property, and that we're just going to call it as linear independence. Okay. So if we can check this, then the uniqueness part of the basis would be true. Okay. So with this definition, what we end up saying is, here's the second definition, out definition of basis. If span of a basis is V and B is linearly independent, then we say B is a basis for V. Okay. So that because we took out the original understanding of what a basis is and split it into two properties. One is that you can represent any vector in V as a linear combination, and it should be shown, it can only be done in one way. There's only one way to do it, right? So the representation is unique, then it's a basis. That was our original definition, right? But if we split those two into different things, then we have a more compact way of saying what a basis is. But, you know, in many ways, the abstract versions are hard to understand because it's processed. If you only eat processed food, then you're not healthy. You don't have a good understanding. So when you cook your own food, then you have a better understanding of food and you're healthier, right? Just like that. I mean, if you have a subspace, what would you want to do? Like that's like the natural way of how people think, right? Let's say you have a subspace. You have x plus y plus z equal to 0. Okay. Now, what's an efficient way of representing this vector space? Well, one way is to write the equation x plus y plus z equal to 0. That's one way to do it. Another way to do it would be to choose two vectors in this subspace and say I want a times 1, negative 1, 0 plus b times 0, 1, negative 1. If you write it like this, then that's another easy way to represent the space as a linear combination of these two, right? But at the same time, you want the representation to be effective or as economical as possible. And how do you make that work? You want the two vectors that you chose to be linearly independent, or whatever list that you chose to be linearly independent, so that you're not overly representing. You just choose just enough, okay? That's the feeling that you get of what a basis is, right? The problem is, if you open up any linear algebra textbook, it's just going to start by explaining what a span is, what a linear independence is, and then after that, it's going to define that basis is this. I mean, that's clear, but it lacks the intuition of why we would want a basis. Okay? Why do we want a basis? To effectively represent the vector space. That's why we want the basis. Right? And for effectiveness, what would you want? Like, you should be able to represent it, but you should also have uniqueness. Those two list of wants is what makes up the basis. Okay? So you have to be able to think of a definition from two different sides. Okay? Like, even this one, I kind of like explain why we would want such a property, but can anyone explain why we call this linearly independent? What the heck is this? Like, linearly independent, where does that come from? I don't see anything from here. Why would you call this linearly independent? That should be a question. Somebody should have raised their hand and say, Professor, why is this called linearly independent? Right? So let's try to take that part and understand it as it is, okay? So we already have an example of a linearly independent set of vectors, right? What was that? It was 1, negative 1, 0, 0, 1, negative 1, and negative 1, 0, and 1. That was a linearly independent set of vectors, right? Now, why is this not linearly independent? Well, according to that definition, if the only way to make this something times this, something times this, something times this equal to 0 is 0, 0, 0, if this was the only way, then this will be linearly independent. But we know that this is not, because this is length 3 and it spans only the subset V, right? So can you come up with some numbers here that's not 0 that still satisfies this? Come up with such a thing. Well, let me help you out. I want this to be 1 and this to be 1. What goes in here?
1.
1, right? So if I do 1, 1, 1, that does give you 0. So of course, this doesn't satisfy that, therefore this is not linearly independent. So this is an example of a linearly dependent list, okay? So these three vectors make up a list that's linearly independent. But I still haven't explained why we call that linearly independent and this says linearly dependent. So let's try to say this again. What are we getting here? We're saying 1 times V1 plus 1 times V2 plus 1 times V3 is equal to 0, which means you can say V3 is equal to negative V1 minus V2. Or another way to say it is V3 is negative 1 times V1 plus negative 1 times V2. Right? You just move V1 and V2 to the other side and then you write it like this. And see what happened here. I've represented V3 as a linear combination of V1 and V2. You get it? Okay, so V3 is a linear combination of V1 and V2. Right? Anytime you have such an equation, something times V1 plus something times V2 and something times V3 equal to 0, with not all of these 0, then what you can do is you can take the non-zero part and then solve for that vector and represent that vector as a linear combination of the other guys. And if that's the case, wouldn't this be natural to say, oh, V3 is linearly dependent on V1 and V2? Does that sentence seem natural to you? Let me repeat what I just said. V3 is linearly dependent on V1 and V2 because I'm able to express V3 as a linear combination of V1 and V2. Does this sentence make sense as an English sentence? Right? Being able to represent as a linear combination seems to be very fitting for calling it linearly dependent, right? Okay, so that's where this definition is from. So an alternate equivalent definition would be to say that, so the alternate definition of linear independence is to say, if some Vk in V1 through Vn can be written as a linear combination of V1, V2, Vk minus 1. I mean, you can't include Vk itself, so I'm going to be, I'm trying to skip Vk. That's like a complicated way of saying this. Then we say Vk is linearly dependent on V1, Vk minus 1, Vk plus 1, Vn, okay? So that's what we say, linearly dependent. If no Vk is linearly dependent on others, we say V1 through Vn is linearly independent. Okay? That's more in line with this word linearly dependent, linearly independent. Okay? But you see, going from this definition to this or vice versa is not so easy to see. You can only see it after writing down explicit examples. You can see that, oh, indeed, they're the same thing. Okay? And if I take everyone who just took MAT 211, Intro to Linear Algebra, you learn linear independence there, okay? And I just choose a random person and ask, explain to me what linear dependence is or linear independence is. I think 80% of that group is not going to be able to explain what they just understood, what they just learned in that class. That's why this class is so hard, because you're supposed to learn some things, but you only learned how to calculate, you didn't learn the concepts. Now you come to MAT 310 and just everything seems to be so confusing. Okay? And that's why it's very important to understand the concepts that I'm trying to explain here. You learn all this in the context of Rn, in MAT 211. You're going to redo this in a more abstract setting, and you have to have the intuition. If you don't have the intuition, then sorry, you can't do the abstract proofs. Okay? You need the intuition. Okay? Make sure you have the intuition.